Today we're going to speak about ROP shellcode discoveries. We were involved in shellcode discoveries in the course of several years, together with Ivan and every time, and all the presentations and conferences we have presented our work. We've been asked the same question over and over again: do you know how to discover ROP? So then we started answering this question. Yes, we do. A small suggestion. What is shellcode? Well, shellcodes traditionally are some malicious executable code which exploits errors of work with memory corruption. Traditional shellcodes are errors of buffer overflow, stack overflow, and any other overflow structures. All the errors which are related to the memory can be considered the shellcode errors. And well, basically, this is a small example of how it works. We have some kind of a code. We have some kind of a code which calls a function. Function waits for the insert of a certain data, a certain line which has to be introduced, where the user transfers certain data. So what happens on the stack at that moment of time? On the stack, they store the return address, which points on the next instruction behind this function, then stores registries and selects certain area for local variables. And the main idea of the fraudster is to rewrite this area of local variables to rewrite the return address. Then we transfer the control to the recorded shellcode, and then we execute this any code. Well, I would like to say that this is a very standard race condition between those who write these exploits and those who produce operational systems and people who try to write detectors of those exploits. From the point of view of the mechanism of memory protection, the simplest shellcode in modern operating systems is not going to be executed so simply because on the level of OS, we see more and more complex defense mechanisms from exploiting errors of memory. Well, first of all, the stack canaries, as they are called, the simplest one. With this in mind, they calculate some pseudo-random value, which also is put in the stack before the registers that been stored. When exiting the function, this pseudo-random value is stored in the area of data in some place. When leaving this function, these pseudo-random values are compared, and if it's a wrong one, the process terminates. Well, everything looks wonderful, but this is not a solution from shellcode, because first of all, right now, in any way, you can calculate or apply any other, like magic, and find out about these cookie values. And I've seen situations when this was simply a static value or a certain constant that was used. Well, you can rewrite this cookie in a data section directly, or you can intercept this exception handler, because when you do the termination of a process, the first thing that Windows system looks at, it tries to understand, do we have a certain rewritable custom handler? If we are able to rewrite it, then we can execute this shell code. These shell codes are called oriented exception processing shell codes. Well, there are methods of protection which allow us to discover in those things. Instead of stack protection, we try to protect the exception executor. So what is the way around? Not to use SEH-based exploits, which are looking at rewriting of those exceptions, and find a module in the application that is being compiled without utilization of this flag, save SEH, and then it's going to be executed. In addition to that, it's very popular right now to the non-executable memory, so direct data execution in the stack to prohibit the execution of the stack. There are software realizations of this protection, there are hardware realizations of this protection, and namely the solution of this problem for the fraudster is ROP shell codes that I'm going to speak about in this presentation. Well, what is the main idea here? To build a malicious exploit from the set of legitimate variables and legitimate code pieces, and I will tell you in more detail later about it. And right now, in practically all systems, there are means of protecting randomization of memory of the address space and processes, stacks, piles, and everything else. But nevertheless, this also can be gathered around because you can find some other vulnerabilities which can disconnect this mechanism of protection, or will define a more complex vector of attack or apply ROP shellcodes. ROP shellcodes, return-oriented programming, as I've told you, allows to get around certain defenses, certain mechanisms of memory defense and level of the operating system. And once again, we build our malicious code out of this set of legitimate codes out of system libraries and functions which are present in the address space of the executable process. For example, the simplest shellcode of a similar type, let to leap, in a stack, in this case, we don't put the malicious code. In the stack, we put a number of addresses which transfer the control to, for example, a function which exists somewhere in our system. For example, we transfer the control on this function. We record its arguments into the stack. Then, when this function has been returned, we disconnect a non-executable stack, and then we can transfer control of our code and execute it. More complex process of building such programs without usage of return of existing functions is a ROP shellcode. So what is the idea? We have a certain set of gadgets. Gadgets are very limited set of instructions before the let instruction in system libraries, before ret. Then we put a number of addresses of those instructions to which you have to transfer the control. And when the rep is being called, you will pull from the stack the address of the next instruction. Therefore, for these small pieces of system library functions before the return address, we will have the malicious code built, and that's how it works. And in the previous example, it was the same thing. We store the address and we store the arguments of this function. Well, approximate example how the ROP shellcode will look, which was built from the libc library. Small gadgets before return function, then we transfer the address of this gadget, we execute it with the argument, rep function pulls the next address, the ret function pulls the next address. Well, honestly speaking, as for the means of discovery of ROP shellcodes, everything is very bad from this point of view, because with the traditional shellcodes, we have figured out how to fight, and with x86 shellcodes and ARM shellcodes, we can discover that we have a number of static methods, a number of dynamic methods, but unfortunately, ROP shellcodes today is a big headache for all of us, and for the industry and for researchers. And there are several means which are trying to solve this problem somehow, but they do have certain deficiencies, and we'll speak about those deficiencies a little bit later in our presentation. The criteria of comparison, on the basis of which we've been comparing those methods, is type of analysis, external or internal type of analysis, external analysis, which is not involving the executable process, internal analysis, when we inbuilt into the analysis and the compilation process, and then we get inside of the process that we try to protect. The methods of analysis, they can be static, they can be dynamic, possibility of tracing of the software protected, and the necessity in the initial code or the debugging information. Well, briefly, I would like to tell you how these methods look like. For example, there's a method like ROP scan. ROP scan does simulation of the code execution. In other words, it means the code is not being touched itself, it's being executed in a virtual environment. At the same time, we do create certain 4-byte window, and we do look at our incoming buffer as an incoming data, and then we're sliding in the 4-byte window and we're searching for the first gadget, which can be the first entry gadget into ROP shellcode. So we're looking at a set of valid addresses. After we have discovered this first gadget in the statistical analysis, we start emulation of its execution. Upon the results of the execution emulation, we'll look at how many times did we hit the address space of the valid addresses, how many times we have executed the ret function, and in the same article, we have shown big research from the point of view of how how many transitions should there be through the RET in gadgets in the malicious programs of shellcodes instead of random data? So in the random data sets, we never be able to see 4 sequential transfers on RET instruction. 4 sequential transfers. So this is a strict threshold for the discovery, 4 RETs. The ROP, it's another method. They said that we will look dynamically for a certain code which looks as ROP shellcodes, and then we'll transfer it into a shellcode which doesn't use ROP. So they basically translate a language. They translate the software in a software which doesn't use ROP. Then they give the existing code to the analyzers of existing ROP shellcodes, whether 86 processor or RAM processor or anything else. So you have found something malicious, and somebody else should do it for you. The ROP stop methods. It's modeling. On the basics of statistical analysis, code statistical analysis, code of the protected program, we build an 8 automation of its all possible conditions and how the software should be executed. Then we will build the graph of instructions flow, management flow, values of registries are being developed, and then after this we do the emulation of execution of malicious data and suspicious data. If we have deviation from the main model that was built in the beginning, then as a consequence we stop execution. ROP methods. Well, it's a very complex on the screen, but briefly speaking about it, by statistical analysis, we search for possible gadgets, and analysis goes on the basis of which possible number of instructions are present in the gadget. In addition to that, we have noticed that in legitimate programs, after transfer from RET instruction, we can go to totally different areas of memory. In other words, when we speak about ROP shellcode, we are not localized only in one library or in one limited address space of the executable process, because ROP shellcode construction is a very complex process, and nobody will jump from one memory space to another memory space. So the same way, they are looking at the distribution of addresses after transfers to RET instructions. So this is the main trigger to ROP. Will it be a ROP shellcode or not? ROP Defender. It's the defense instrument which use shadow stack in its analysis. So by statistical analysis, we have to look at the buffer of suspicious data if the call instruction or any other instruction has been called, after which possibly there will be a possibility to pull the next address. We pull it into a shadow stack. After this, by statistical analysis, when the execution is happening, we look the difference between the original stack, which is the under control of the ROP shellcode, and a shadow stack, which shellcode knows nothing about. If there are deviations between them, then of course the process is also halted. On this slide, you can see results of our overview and a number. Well, the performance of some systems is in the throughput capacity defined. Some systems' performance is defined by how strongly the analyzed processes are slowed down. So speaking about the errors of first and second type, I always look at these numbers very skeptically because, well, this is what authors say. And for the shellcode sample they have been providing to us and they have been analyzing, this is true. Speaking about other ones, they have not analyzed them yet, I think. Well, I will give floor to Ivan right now, and he's going to tell you about what was done by us in our work, generally speaking. Well, upon the results of the overview that we have done, we have selected main deficiencies of existing means of defense, and this overview has included only those means of defense which don't require further analysis the initial code of the protected program, because this property is not executable in real practice. So let's go to the deficiencies of those products that have been overviewed. The main ROP scan deficiency is the fact that this system does not look at pages of memory that were selected selected to the process with the help of SLR process. As it was noted before, the SLR technology is a technology of memory protection, so-called randomization of memory. The memory segments such as libraries, stacks, or piles are selected to the process by certain random addresses, in order for the attacker not to be able to define their location in advance. At a given moment of time, there are methodologies of getting around of these methods of protection, and we can make an example. For example, even a program, there's availability of memory leak. The attacker can exploit it and discover the address of a certain library function. By using this address, he can calculate the shift on the basis of which the process was allotted a certain library, and by this, he can use this library as the source for the ROP shellcode addresses. Which leads us to the situation that it's possible to write a shellcode which will not be detected by ROP scan system. The main deficiency of the ROP system is the fact that shellcode acquired after the transformation is not a pure copy of shellcode whose functionality was defined by the given shellcode, which leads us to the following situation. In the given shellcode, we may not use certain specific techniques which are used in original shellcode and to which other means of discovery of shellcodes are reacting. Therefore, the further application of these techniques will not lead us to positive results. The main deficiency of these systems like ROP stop, DROP, and ROP defender is the problem that discovery of the shellcode happens only after it was put into address space of the process, executable process, and in order to stop the malicious activity of the shellcode, the only way to stop it is halting the program. Therefore, these systems, they cannot be used in environments which require high file resistance of the systems. Also in our work, we have done analysis existing ROP shellcodes that were discovered in public exploit databases and special generators of ROP shellcodes. On the basis of this analysis, we have discovered main signs of ROP shellcode availability and they can be divided by statical and dynamic signs. Well, by the way, I would like to make a reference to our previous work because the mean of shellcode discovery on which we are working because of the next several years is discovering shellcodes by certain signs. So we discover shellcodes on the basis of searching in a flow of input data a certain set of signs and certain lines. But we decided not to get away from this idea. We decided to complete this module of this existing product. So that's how we are trying to look for signs specific for shellcodes, which differentiate them from legitimate traffic and any other types of shellcodes. So let's go and look at those signs. One of the statistical signs is the availability in the network traffic, so-called valid addresses. Under valid addresses, we understand addresses which show to the pages, first of all, given to the process, and second of all, to the pages which allow us to execute instructions. Due to the fact that shellcode, ROP shellcode, is being constructed of addresses of gadgets and their arguments in ROP shellcode, we will see the presence of these valid addresses being present because those addresses are addresses of those gadgets out of which ROP shellcode is being formed. Therefore, availability of these addresses in the input data can signalize us about presence of the ROP shellcode. The next statistical sample is the availability of the addresses which show to certain code gadgets. And I will repeat that code gadget is a certain sequence of instructions of a vulnerable process, and this sequence which is ended by a certain construction of transition which can be a controlled process by the attacker one. For this process they use a return instruction, ret. So we disassemble the address space of the process and we search for the given gadgets. Then we deduct from the address of return certain maximum value of the gadget, and it happens that our address space is being divided into gadget intervals. Therefore, in the input data, we can do the search of addresses which belong to the given interval. Also, I would like to point out one important fact. Not every address which belongs to this interval is a gadget's address, due to the fact that in the architecture of x86 the sizes of instructions are different. During disassembling with various shifts, the return instruction can become a part of a certain other instruction, which will lead us to the situation that this address will not be an address which shows us to the gadget. So we have to check the validity of these gadgets. Let's go to dynamic signs. These signs are signs of ROP shellcode behavior. Dynamic signs are being analyzed by a certain virtual environment during emulation of ROP shellcode. For example, one of the dynamic signs is a sign of number of executed returns that were executed during emulation. Under returns, we do understand a number of executed instructions return, which gave control to a certain valid address. This number can describe the number of gadgets that were executed during execution of this ROP shellcode. In other words, first address gives control to the first gadget that is being executed, this user load, and then return instruction redirects this control to the second gadget. In other words, we can calculate how many of those returns were executed, and then we can put a certain threshold in order to cut away in advance wrong parts of the code. The next dynamic sign is the availability of system calls that were done during the emulation. Due to the fact that attacker needs to control the attacked system, he needs to use certain system sections. Therefore, by simple solution will be checking of a number of system calls that were done during the emulation. And I would like to point out that it is necessary to check validity of initialization of those arguments of these system calls. What do I mean by that? For example, if one of the arguments of the system call is address, then it is necessary to check that this address was allotted to a given process. And then the same thing to other arguments. So every system call has to be correct. These properties should be checked due to the fact that in data from the networking traffic, there can be addresses which truthfully point to certain system calls, but at the same time they do not point to a code which correctly will initialize those arguments, so it's not ROP shellcode. The next dynamic sign is availability of attack of return to the library. As we've said it previously, the read to library attack is an attack during which a return address has been recorded not to the shellcode address but to the address of a certain library function, with the help of which attacker wants to get around the memory protection. For example, address gives control to the function mmap, which selects vulnerable process, gives a certain memory section where the instruction can be executed. Then the instruction is being called, of data copying instruction is being called. It copies shellcode from stack, non-executable stack, to a new allotted section of memory where it is permitted to execute this instruction, and then transfers control to it, therefore, by this starting shellcode. Therefore, the main sign will be the fact that during emulation, a certain new page was separated, which allows execution of the instruction, and then control of the program was given to it. The same is related to already existing pages, because the shellcode can change the access rights to the existing pages and therefore disconnect stack protection. Right now I would like to tell you about the previous work we have done. Also, I will be brief, but I have already told you about that. In other words, we have certain set of detectors and signs which are able to discover in the input data shellcode signs. We put them in a certain topology which allows us to effectively separate legitimate traffic from potentially malicious one. And the simpler a sign is, the higher it's going to be located in this topology. In other words, potentially malicious shellcode or suspicious code, the more suspicious it is, then it will go to the more difficult detectors. So each detector can tell you that this sign already is not executed, then it's not a shellcode, and then we just return, in given case, the package to the channel reversely. It has reduced us the number of auxiliary costs and computation complexity of the system, and the work that we do right now with raw shellcodes has been done in the framework of the module of this system, Dimorpheus. we also have realized a detector of signs of shellcodes, and we put it in this general topology, dimorphies. So in our work, we have developed means of discovery of shellcode in networking traffic. This product does the analysis of the networking traffic and the availability of ROP shellcode in it. In order to do this analysis, it is necessary to have access to the address space of the vulnerable process in order to be able to reconstruct ROP shellcode from incoming addresses and analyze it afterwards. The first solution that we discovered, it was a simple connection to the process of a debugger and then reading of the information with the help of system called ptrace. After we have realized that, we have understood that we have big auxiliary performance problems in the processor time, because in the analyzed data, and we have a lot of those, and system called untrace gives this limitation to us. Therefore, it is necessary to solve a problem of providing a system with a direct access to the address space of this vulnerable process. The first thing that comes to our mind is a direct copying of a page of the address space of the process under control, but the given solution gives certain limitations to the memory, because protected processes, we can have a lot of them, and they can take a big part of the operating memory. So copying of those pages of this process will lead to even bigger overflow of the operating memory. Therefore, we came to a decision to copy these pages with the help of copy and write technique. What is this technique is all about? The system call fork uses it to copy address space of the protected process of the parent process to a daughter process. The system call fork is not copying this address space of a process immediately. It copies it only page by page, and only when certain pages had write operations. For example, if we have a page which belongs to a parent process, a system call fork will copy it to the daughter one, but physically this page will exist only in a single copy. Therefore, we have decided to use this technique. The first solution was to use a Linux core that will use a processor of system fork process in order to be able to copy the other process, but we have seen an obstacle as a macros account process, because the system calls are executed on behalf of a certain process, system process executor shouldn't look at the descriptive process to copy it. It looks at the existing process through the current process macros. Therefore, we have decided to use the technique library injection. In other words, protected processes, in them we load so-called agent library, which during the load calls the fork system call. By this, copies the protected process, then removes itself from the OS and returns the control to the protected process. In the daughter process, this library starts a process of creating the emulator. In other words, the emulator library is being loaded, which is responsible for dynamic analysis and emulation of ROP shellcode. After this, the daughter process goes to a sleep until the moment when dynamic analysis will be required. The analysis of the input data is being done. The input data is being divided into intervals, 4 bytes each, address and memory size, and each of these addresses is being redirected to statical and dynamic analyzers for checking. Statical analysis is searching for the gadget to which the input address is showing, so the gadget of the code which is a part of the ROP shellcode. This search is happening in 3 stages. On the first stage, we see the checking of the validity of the given address. So the given address is being searched in non-valid memory. This point, we need to be able on the early stage to cut away the addresses which are not addresses of those gadgets, because they are not specifying the valid memory. If the address of the checked validity is completed, then we search for a specific memory page which shows to this address, and then in given page we do the search for a gadget to which this address is pointing. So let's look at each point in more detail. In order to be able to remove addresses which are not gadget addresses at the early stage, we built a black and red tree of intervals on non-valid memory. Under non-valid memory, we understand addresses which either are not selected to the process, not given to the process, or given, but they don't allow the execution of an instruction because we need pages for the gadgets. So each interval is given a certain node in this red-black tree. And also I would like to point out that non-valid addresses, well, we have more of those than valid addresses. Therefore, this tree will not go through all the depth to the page in order to understand that the address is not valid. And if the address is valid, then in a search tree, this address will go to a certain page, and then afterwards more complex analysis will be applied. In order to discover page in a memory which belongs to the process, we also use the red-black tree, but of valid addresses. Valid addresses are put as nodes in this tree. And for every page, in advance, we do the disassembly and a search for gadgets. These gadget intervals are given to a certain tree and a node of the tree. By this, we can go through this tree and discover to which gadget which address belongs. Also, I would like to point out that gadgets which follow one another without any pauses are united to a single node in order to reduce the number of nodes in the tree. After a specific gadget has been discovered, then we check for the validity of the given gadget, as we have pointed it out previously. Due to inequality of the sizes of the instructions in 86 instruction, during disassembly of a return instruction, it can become a part of some other instruction if we will disassemble with wrong shift. In other words, we have to, for every gadget that we discover, we have to start disassembling, and we have to check availability of return instruction in it. And you can see a couple of examples when return instruction is being disassembled correctly and given sequence of instructions becomes a gadget and incorrectly. After the stage of statistical analysis, we have certain information about which addresses are showing to gadget addresses. These addresses are given through dynamic analyzer in order for it to be able to analyze ROP shellcode and analyze its behavior. Due to the fact that we don't know in advance which of the addresses will specify the first gadget of ROP shellcode, emulation begins from each gadget. During emulation, we collect statistics about operation or work of the ROP shellcode. Upon listed dynamic, we collect information about dynamic calls, system calls, number of executed return instructions, validity of addresses to which they make transition, and also attacks of return to the library. On the slide, you can see an example of the work of the emulator. On the left side, you can see the stack where the input data was introduced, and in the red color, you see the address of the first gadget from which ROP shellcode is being started executing. In different colors, you see different arguments which are being used for the registries. For example, in purple color, these are arguments for system calls. So, after stages of statistical and dynamic analysis, it becomes possible to localize packages which store the malicious code, and on the basis of this information, we can make decision about removal of these malicious packages. The system that we have developed, it was tested on a test sample which consisted of ROP shellcode and voluntarily data. The ROP shellcode selection was done out of existing ROP shellcodes which were discovered in public exploit databases, and shellcodes which were generated with the help of special generators of ROP shellcode. The testing have shown us that upon the criteria of errors of the first and second type, system that was developed is not worse than existing analogies, which is also good. Also, we have done testing of performance of the system that was developed. As a protected processes, we have selected popular applications for a service like Apache, Nginx, OpenSSH, PostSQLite. Testing of performance have shown us that the system that was developed by us has more performance than existing analogies. In a given case on this slide, you can see the existing analogy which uses the same type of analysis, the external analysis. So, brief conclusions about the work that was done. We have developed a system of detection of ROP shellcodes in high-speed networks. This product has a number of advantages compared to the existing analogies. And among those advantages are high speed of data processing, independence from the availability of the source code of protected program, availability to discover ROP shell codes which are getting around ASLR protection, and another advantage is the fact that to prevent the vulnerable activities of ROP shell code, you don't have to halt the program that is being executed. And briefly, I would like to list the main points of the work that was done. First of all, we have done analysis of the existing methods of ROP shell code systems, and we have discovered their main deficiencies. Also, we have done analysis of the existing ROP shell codes and generators of those. On the basis of this analysis, we have selected main signs of availability of ROP shell code in network traffic. On the basis of these signs, we have developed a product of discovery of ROP shell codes in network traffic. This product was tested on real data. Well, that's it. Thank you very much for your attention. Well, if you have any questions, please ask them and we will answer.
Лаборатория Касперского. Хотелось бы узнать, на каком этапе вы производите внедрение библиотеки агента? На старте процесса или при получении каждых входных данных?
Не при получении, мы делаем это заранее. То есть как только запускается система, она запускает в ядро Linux модуль для ядра, который предоставляет ей всю необходимую информацию о текущем состоянии системы. Далее определяются процессы, которым требуется защита. Например, процессы, которые взаимодействуют с сетью. И далее в данные процессы внедряется библиотека агент, которая уже начинает этап создания эмуляторов. Эти эмуляторы погружаются в сон для того, чтобы в дальнейшем
Является
то, что для анализа не требуется.
It's not required. Well, only reading from the address space is needed of the defended process. And due to the fact that we use copy and write technique, physically in the memory, this address space in these processes is present only in one copy, and it's not being copied. It's not being copied due to the fact that for the analysis we need only reading from the given pages. So these emulators are being created. They have direct access to the address space. They don't have any delays for the reading from the memory, and these processes are put into sleep until the moment when we will need certain dynamic analysis. So until that moment, if certain address will go through the whole stage of statistical analysis, it will go through the validity of the gadget check, and only then, if a more complex check is needed, these emulators will be started. Then I have the next question. For example, if address space of a process was able to change after you have done a fork, but before the execution of the shellcode, this property also is being checked, and actual information is always being updated. So at any moment of time, you can remove the old emulator and create a new one. So you do the monitoring over the address space. Yes, we do. We definitely do. Thank you. Unfortunately, we have not analyzed coded traffic, encrypted traffic. More questions? The question is not being asked into the microphone, therefore I cannot translate what I can't hear. We don't do halting of this process. This stopping of the process is used by the means which use internal analysis. So the analysis of the software behavior, where the ROP shell code can be a part of. As we have shown in the overview, there are products which are getting connected to the process. They have certain model of the program operation, and they check for deviation. Our program catches them on a level of network, catches those packages on the level of network. So these packages are not even entering the protected process, and by this there is no necessity to halt it. So we analyze traffic and we analyze shell code on the process of its transportation. And in this stage, the package is being removed with the malicious code. Did you have any interesting false positives, and how you've been fighting against them? With false positives and ROP shellcodes, there's a special peculiarity because even all existing means of discoveries, false positives are on the level of 0, and this property comes from the fact that the number of executed returns is a very strict threshold for cutting away the vulnerable data. We had several researchers before us which shown us that random data, no more than 4 returns, returns which follow one another, no more than 4. So the sequence of calls of ROP shell call gadgets, no more than 4 returns. That's why we do the threshold. So we speak about more about false negatives, false positives. In ROP shellcode cases, it's very easy to find it due to this heuristical work. But as other people, most of the people here, they know certain detectors and they've been writing about those detectors, and you know that there's a simple heuristics which can cut away and differentiate legitimate traffic and some legitimate objects from non-legitimate ones. In our case, we've been speaking how to fight against false negatives. That's it. Question is not being asked into the microphone, so I do not hear it. It depends on the number of gadgets that were discovered in a given process. The more gadgets you have, the more probability is that given address will be in a list of these gadgets. I don't hear the question. More questions? Then, thank you very much for your attention.